Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello, good morning, everybody. So it's a great pleasure to have our good old friend and colleague Rich from Redmond coming to us today and talking about depth. He's got a lot of background on both decision forests that we love here in Cambridge, and also deep neural networks, which are a little bit less familiar with in Cambridge. So hopefully he will help us bridge the gap. Thank you very much.
Okay, thanks. So it's great to be here. It's very nice to see the new building. So the last time I was here, I think it was just a month before you were going to move from the old building. So this is a really nice facility. And we should definitely just watch movies here tonight. This is quite a room. Okay, so I'm going to talk about some work I've been doing in trying to understand deep learning. And I should be honest, before I start this, I'm not a super expert in deep learning. It's not like half of my research is in deep learning. But I've been a neural net guy for a long time as part of my work. When the deep learning stuff started to happen, it raised some interesting questions that I wanted to try to answer. Okay, so this is joint work with Jimmy. Let's see, so how many people have trained neural nets, or at least feel like they're pretty comfortable with neural nets? Okay, that's good. So this is a shallow neural net. This is the kind of neural net that we were all training circa 1990. It's got an input layer, a fully connected nonlinear hidden layer, and then an output or multiple outputs. This is a shallow standard neural net. It's the kind of thing we were all training for a long, long time. For 15, 20 years, these are the neural nets that ruled. This is a deeper neural net. Maybe it's the shallowest model that we might want to call deep. So it has 3 hidden layers in it. So they're just fully connected feed-forward connections. Each of these is a nonlinear hidden layer. And as neural nets do, they're trying to learn a new representation on each of these layers to then support predictions at the output. And this kind of model, this shallow deep model or deep shallow model, is also something that many of us played with back in the early 90s. But for the most part back then, we didn't get any extra accuracy out of these things than we did out of these things. And if we did get a little extra accuracy, it was small and usually not worth the incredible hassle and expense of trying to train them. So by and large, this is what everybody did in the 90s, with one exception, which is this model on the right. This is a convolutional deep neural net. So now what makes it a deep neural net is that it has these multiple layers, multiple nonlinear layers like this middle model. But what makes it convolutional is that it has this convolutional layer or set of layers at the input of the network. So how many people are familiar with convolutional neural nets? Okay, not quite as many. I'll just give a really brief summary of what they do. This model is also, except for the fact that it's got 3 layers on it, if it was this convolutional input attached to one nonlinear layer, then this would be a common model also from the 1990s. So Jan LeCun invented this a long, long time ago. And it's been a very powerful model in certain classes of problems, things like image recognition and classification. So let me just briefly explain what convolution does. Let's see. Suppose you were to try to take this model or this model and try to train it to recognize faces. And let's imagine that it's sort of natural scenes where the faces can occur in different parts of the image, and you're trying to recognize, is there a face in the image? If there is a face, maybe where is it or who is it, something like that. This kind of model, it doesn't know anything about the adjacency of pixels. If you give this a 100 by 100 pixel map as an input, it just sees that as 10,000 independent inputs. It has you can sort them in any order, it doesn't matter. It has no idea that this is, in fact, a 2D representation of an image. And because of that, if it learns to recognize faces, it has to separately learn to recognize faces in the middle of the image, in the upper left-hand corner, at the top of the frame, and the right of the frame. It has to see enough data with faces in all parts of the image to learn separately to recognize faces in all those different places. And hopefully that just sounds like a terrible thing, right? If I give you sort of a lot of faces in the middle and then I go to test you on a face that happens to be more off-center, it won't recognize it because it never saw faces there, or at least it never saw enough to learn a good model there. So that's not a good thing, right? I mean, faces tend to look the same wherever they fall in the image, so that's not a desirable property. Also, you'd really hate to have your training set have to be so massively large that there was a statistically large sample of faces for every position in the image. That's a painful thing. So of course what we would do is we would do tricks. And those tricks would involve sort of external for loops. One thing we would do is we'd have the face recognizer only look at a small sub-image, maybe 10 by 10 pixels, and then we would scan that 10 by 10 window across the entire image. And whenever a face was sort of somewhere in the middle there, we would label it 1. And when a face wasn't centered enough in that image, we would label it 0. And we would train a recognizer now on centered faces, or something close to centered faces, faces that show up in this box. So that loop would be done externally. The neural net has no idea that you're doing that to it. It's just that you've sort of increased the size of the training set. Right? We had this problem that the training set would have to be sort of massively large if it was natural images to make sure it had faces everywhere. Now what we're doing is we're making it massively large by creating all of these training points where we've scanned all possible places in the image. And then we would also do things like change the scale at which we would do the scanning. Maybe we'd magnify the image by 1.5 or 2, or demagnify 0.75 or 0.5 before doing that scanning. So then we could try to recognize faces of different sizes, different distances from the image. So we would do that sort of thing, and that worked fine. So we would get reasonably good accuracy out of it. You can imagine if you've got a large frame that it now takes some real effort both to train the model, because you have to train it on this very large training set, and then also to run the model, because you're going to have to scan it across the image many different positions in order to try to detect the faces. But that's how most face recognizers that use neural nets worked in the 90s. Now convolution is kind of interesting in that instead of doing this external for loop where we're scanning over the image, convolution lets us put that sort of knowledge, that structure of the image, into the model. And think of it as each hidden unit, say in this first layer, take that hidden unit right there. That hidden unit has a retina which sees a small subpatch of the input image. So right away, the fact that I say subpatch means that it knows something about the structure of the image, that adjacent pixels are adjacent to each other, right? So, and it's up to the engineer to have told the model, oh, I want you to look at adjacent pixels in a 5 by 5 patch of the inputs, things like that. And then what that neural net will, what that node in the neural net will do is it'll learn to recognize for that patch features that hopefully are going to be useful for recognizing faces. But what's important is it'll learn it not just for the sort of patch which you might think is falling under it in the inputs. It'll learn it, it'll be scanned internally in the learning algorithm. It'll be scanned so that that patch applies everywhere in the image that a 5 by 5 patch can be made to fit. And in the process of doing that, it'll learn one set of weights for predicting that feature, for learning that feature. It'll just learn one set of weights for that feature for the entire image. And it'll automatically be applied at runtime, at prediction time, to the entire image. And wherever it sort of goes off the most, there's another layer after it called a max pooling layer, which would then detect that it's gone off the most and would say this feature is high. And then you might have another layer of convolution. If these are all little small features with local receptive fields, there's another convolution layer that's higher that's looking at maybe a wider set of these smaller receptive fields. And you can imagine that the sort of feature space grows to be larger parts of the image as you go higher in the hierarchy. Okay, so that's a convolutional model. And Jan LeCun, would often have 2, 3, 4 layers of convolution in the model. And it was something that the engineer would sit down and think hard about the problem, think what convolutional architecture kind of made sense. Just like here, we would have figured out how to scan appropriately across the image. Then you would build the architecture that way and you try it. You'd repeat a few times until you really got it right, and then it would learn to do it. Okay, so this is a shallow model that's been around forever. Deeper model has been around forever, but we just never had much success with these things until recently. And then this is a deeper model, deeper because it not only has these nonlinear layers, but because it has these layers of convolution on the input. In this case, just one layer of convolution and pooling. So, okay, and it'll turn out we're going to be using these models, which is why I use these specific examples. Okay, today what I'm going to do is I'm going to mainly talk about results on the TIMIT speech recognition data set. So how many people know TIMIT or have even used it? Okay, so a couple of you. So TIMIT, it stands for Texas Instruments and MIT Speech Recognition Corpus, right? It's a data set that I think has been around 20 or more years. So this would have been one of the early large data sets that people were doing machine learning with. So this is a well-established data set. People have been working hard on this data set for a long, long time. And it really was sort of the early standard for anybody who is doing speech recognition, was to work on this data set. So we're going to use it for two reasons. One, there's been results for a long, long time. But most importantly, there's been new exciting results with deep learning on this data set, so that's important. The other thing is it's big enough to be interesting for deep learning, but it's small enough to be practical to run a bunch of experiments. So that's part of why we're using this data set. I'm not a speech recognition person. We have other people at the lab who helped us do the right things with this data set. So let's see, just to give you a brief idea. So what do we got here? This is a visual representation of speech. This is like a second or two in time, and then these are frequency banks going up vertically, low frequency to high frequency, and then this is the power over time that shows up in those bands. And this representation, what we'll be doing is we'll be slicing this into small vertical rectangles, and then that'll become the input vector that's given to the neural net. And the neural net will be trying to recognize phonemes. What phoneme is being spoken at this moment in the speech? And then by recognizing a sequence of phonemes, you can try to put those phonemes together and figure out what words are being spoken. So that's how people use this. I'm told that people who work in speech recognition a lot and work with these things all the time, that they get to the point where they can just look at this picture and they know what's being said. So they get that good at it. So it's a really good representation. And it's kind of like an image too, right? And it works very well even with our visual system. So if all of us had been born recognizing speech this way, presumably I could be giving this talk in these colorful graphs, and you'd all immediately recognize it. So, okay, so let's see. It turns out that the inputs that we're going to give it, we've got about 25 milliseconds this way. I think it's 40 feature banks. Is it 40 filter banks that we're using? Oh yeah, it's even on the slide. Good. And I think that gives us about almost 2,000 dimensional input vector. And then the output vector, which is the phonemes that are being spoken, that's coded for in this triphone kind of way. So it's actually more than it's 3 times the number of phonemes we're actually trying to predict. This is a way of getting some, it's almost like a very cheap form of ensemble. It's a way of getting some redundancy in the coding and letting the model try to recognize a more sophisticated version of what it's seeing. It's not going to be important for the presentation, but that gives us an output which is 183 dimensions. And then there's a well-defined train set, development set for validation purposes and test set for this data. We've got 462 speakers in the train set, another 50 in the dev set, and then 24 in the test set. And I think the way this data set works, correct me if I'm wrong, I think each of the speakers speaks a standard set of sentences. And then that set of sentences is the same across all of the speakers. So if I understand it correctly.
The 183 dimensional, is it just a real vector or is it a class, 183?
So yeah, it's a good question. It's a class. It's Boolean. There's a 1 and a lot of zeros. Yeah. And feel free, of course, to ask questions. Okay, so the train set gives us about 1 million frames of input, and then you can do the math. The validation set and test sets are smaller. Okay, so that's the data we're going to be using. As I said, it's a data set that's been around a long time. And people worked on this hard. As far as I could tell, it was the standard data set for people doing speech recognition. And the best model turned out to be this Bayesian hidden Markov model that was created in '98. And that model has, about 25% error rate. So it's a hard learning problem. And that model was very, very good. And once they got to that point, basically little progress was made for 10 years. So people had worked on the thing. They kept doing better, better, and better. They got to this model. This model had about 25% error rate. And then that record's basically the field asymptoted. They found it very difficult to do better than this. It's not that people stopped working on it. They just couldn't do better. Then somebody applied deep learning to it. They added a deep neural net. I think it might be a 3-layer deep neural net to the hidden Markov model. Suddenly the error rate drops 2%. That's pretty significant if you've been sort of stuck at an asymptote for a decade to have somebody come in and suddenly get 2% improvement. Right? It's not a 0.2% improvement. 2% is pretty big. Then they applied dropout to this deep neural net. It goes down another 3%, the error rate. So dropout, for those of you who aren't familiar with it, is a regularization technique that seems to work pretty well with deep models. So it's a way of randomly allowing the weights to be in or out on each training step so that you don't overfit to any small set of weights. So, and then in 2013, somebody applied a convolutional deep neural net to this. They got another % reduction in the error rate. And then, although I'm not going to talk about recurrent nets at all, we're not going to use this last model, a rumor is that Jeff Hinton has gotten yet another % reduction in error by using a deep recurrent neural net. So I just want you to know that people still work on this data set and are still sort of pushing the frontier for it. But anyway, if you sit back and look at it, right, people work on the thing for a long time. They get to the point where they have what they think is pretty good accuracy, 25%, sort of get stuck. They can't really do better than this model. And then all of a sudden, deep learning gets applied to it. And sort of very quickly, we get a 2% reduction, another 3% reduction, another 1% reduction. I mean, that's dramatic, right? We're talking 5-6% reduction in error, which is not an easy thing to do at the high end of the scale. It's not like we took an inferior method and had a 5% improvement. We took a really state-of-the-art method and have a 5% improvement. So there's something really remarkable happening here with this deep learning. And at the same time that this sort of thing is happening in speech recognition, similarly dramatic results are unfolding in image classification, image recognition. So amazingly good results are happening there as well. Okay, so there's obviously something cool going on here. What I'd like to do is, I'd like to have some idea why it works. And a group of us at MSR got together one day in a room, and we started filling the whiteboard with possibilities for why it works. And it was a long list. It was more than a dozen things that were serious possible explanations for why deep learning was working better than shallow nets that we had used before. So we were wondering, well, how should we go about doing some research to try to better understand this? And I'm going to show you one thread of research that we've been using to attack this. So now the literature has a couple explanations. So one of them, I think Yoshua Bengio probably gets most credit for this, is that suppose I give you a fixed number of parameters. I say you've got 1 million parameters to play with or 10 million parameters to play with for this problem. You have a choice. You can sort of lay them out in one large single hidden layer that's going to be very wide, or you can decide to put less on each hidden layer and you can make the model deeper. And Yoshua Bengio has argued that by making the model deeper, we actually get a more interesting, more complex function class out of the model than if we had put everything into a shallow architecture. And there are some examples of this. For example, parity functions. You can prove that if you're going to represent high-order parity functions in a shallow model, then you need an exponential number of weights in that shallow layer or layers in order to do it. Whereas if you've got enough depth for the degree of parity, it turns out you only need a polynomial number of weights in a deeper model to do it. So at least there are some pathological function classes for which, in fact, you can prove that this is true, that going deep actually helps us in a way that we can't achieve any other way in a neural net, by just staying shallow. So that's interesting. Maybe that's the explanation. Maybe it just really is a more powerful function class. So another possibility is, and it could be that these are related, but let me walk through it because I think the intuition is different behind this one. Imagine we're doing face recognition, and I need to cite whoever I stole these pictures from someone's paper. So imagine you have the input retina, and then the first layer, maybe it's learning something like edge detection, patch detection, small region features. Think of these as things that used to be, say, SIFT features and stuff like that, but now it's all just being learned from scratch. And then maybe a little later in the hierarchy, maybe you're starting to learn small pieces of faces. So those might be parts like eyes, ear, nose, mustache, hairlines, things like that. And then yet further higher in the hierarchy, you're starting to put those pieces together, and you're starting to recognize things that are faces or parts of faces. And then you just go further up the hierarchy until at the end you're actually doing some sort of face recognition or classification. Well, it could be that natural learning, especially if you do learning sort of from the raw input signals to some high-level task like recognizing a face, it could be that natural learning really just tends to have this property that it's easiest, given the kind of sample sizes that we have and the kind of compute horsepower that we have, that it's easiest to do learning if you structure it this way, that you kind of first are going to learn sort of local small features that when combined yield less local, larger features that are bigger pieces of the object, and then it moves up a step and moves all the way until you're at the target sort of level of recognition, which might be faces or bodies or things like that. So it could be that this is just a natural property of a lot of learning tasks especially if you're learning from raw signals. People who work in deep learning will often say, the goal is get rid of all manually created features, go as much as possible to the raw signal, and then learn from that. So maybe when you do that, maybe it turns out that learning just naturally breaks into this hierarchy, and that's just a better inductive bias. It's a better prior for learning. So maybe that's the explanation. It's possible it's just an accident of the training algorithms and methods that we have available right now. So think, I mentioned dropout briefly before, this new regularization procedure that's only come into being. I think Hinton created that in the last 5-10 years. Dropout's a very, very effective regularization procedure on deep models. Shallow models, sometimes it helps, sometimes it doesn't. It's not that powerful on shallow models. So we have a regularization technique that's sort of super powerful in these deep models. Maybe if we had a super powerful regularization technique for shallow models, well, maybe we would do as well with shallow models, assuming these other things aren't true. And there are other things that we've got. We've got a much larger bag of tools available to us now. We have rectified linear units instead of sigmoid functions. We've got all sorts of, we've got pre-training procedures, all sorts of stuff like that. So maybe the reason why deep learning is working so well is just, I don't want to say an accident of the tools we have available, because the tools were created in large part to make deep learning work well. But maybe it's just sort of a perfect storm of technique that is sort of making the deep models work so well. And maybe if we had similar strong methods for shallow models, maybe they would be just as accurate. So that's a possibility. It really could be all the above, right? It could be 20% that one, 50% that one, another 10% that one, and then whatever's left, like 30 or 40%, for something that we don't know about yet, right? So it's possible that that's what it is. It's possible it's none of the above, right? It might be that none of these are really quite right, or if they're right, they're only right a little bit, and they don't explain the main part of why deep learning is so powerful. And you might think, well, maybe deep learning is working because we finally have data sets that are big enough, and because we finally have enough horsepower in GPUs and stuff like that to do it. And maybe that's why deep learning is working so well. A problem with that, though, is, as I'm going to show you in a few seconds, we can't still train the shallow models using all this big data and this horsepower. We can't train the shallow models to be as good as the deep models. So there is something that's happening in the deep models that's not happening in the shallower models. That's interesting. So it's not just a question of horsepower and GPUs. There's no doubt horsepower, big data, GPUs is important to making deep learning work, but maybe it's not the critical enabling thing. Okay. So the goal of this project is just to try to understand why deep learning is working so well. And we're willing to tackle that anyway. I'm going to come clean now. I don't have all the answers. You're not going to walk out of here like, oh, that's it. I didn't see that coming. I wish I had that answer. But we've run into some interesting results, and I think the results are sort of fun, and you'll just enjoy seeing those. And they do sort of give some evidence about what might or might not be the reason why deep learning is so good. Okay, now, gotta be fair here, right? So we're going to be comparing deep and shallow models. Well, again, back in circa 1990, we had theorems which basically said, hey, a shallow model with enough hidden units, enough weights, enough capacity can represent any reasonably well-behaved function. So in the case of parity function, it might require an exponential number of units. But basically, there are theorems which say you don't have to be deep to represent things. So you might think, well, who really cares if shallow can do what deep can do? We already knew that 25 years ago. Well, first of all, this is a representation theorem, which is important. It's not a learning theorem. It doesn't say that backprop will, in fact, learn these things if you were to give it a wide neural net. So, for example, these parity functions are particularly hard to learn. I mean, if life depended on the ability to learn high-order parity functions, we wouldn't be here probably, because it's hard. So sort of a proof based on things like parity functions, is maybe not as convincing as you might want, and it's just a representation theorem. It doesn't really say what's learnable with backprop. Remember, one of the explanations is that there's a good prior coming from depth that we're missing when we train a shallow model. Well, that would be completely consistent with this. I mean, maybe the prior is what's making making deep learning work, and has nothing to do with representational power. So in which case this theorem would apply, but not in any interesting way. It's important to me that we're looking at sort of the functions that we actually need to learn in natural problems. So I'm less interested in sort of pathological corner cases, and I'm more interested in the learning that we actually have to do to get high accuracy on real problems. And maybe it turns out that parity functions aren't very common in the real world, and in fact a shallow model wouldn't have to be all that large in order to learn these things. So anyway, I just wanted to make sure that everybody knows we do already have a proof that at least if you had a magic learning algorithm, a shallow model could do everything a deep model could do if you were willing to give it possibly an exponential number of units. So we're going to try to not give it an exponential number of units. We're going to keep the number of parameters in the model comparable to the number of parameters in the deep model. And then we're also going to use learning. So we're not going to answer questions about what could be represented. We're going to actually demonstrate that it can be learned. Okay. So here's a peek at the results. So here's the TIMIT data set. When we train, this is now our result, not historical results. When we train a shallow neural net, that's like the neural net we had on the left, just one fully connected hidden layer, nothing exciting in it. A good old vanilla circa 1990 neural net. When we train it, we get an error rate of about 23, 24%. And that's actually very good results. I mean, that's comparable to the HMM Bayesian model. Okay, so this is actually quite good. And one of the reasons why it's a little better than people would have gotten 10 or 15 years ago is, we've got more horsepower now. We're a little better at training even shallow neural nets. So it's just a little bit better than things might have been 10, 15 years ago, but not in any surprising way. It's just a pretty good model. If we then go to a model that just has 3 hidden layers, so we take the same number of parameters and we spread it now among 3 hidden layers instead of one wider single layer, we see a 2% decrease in the error rate. So the accuracy jumps 2%. And this is sort of the magic of deep learning, right? Just by taking the same parameters, making the architecture deeper, throwing backprop at it. In this case, I think we are using weight decay. So we're using some of these new tricks for training the model. But all of a sudden, there's a 2% increase in accuracy, which is significant on this kind of problem. And then if we add convolution to it, so we still have 3 nonlinear fully connected layers plus a convolutional layer, we get even more accuracy. We get another % or two of accuracy. And the convolution, the reason, I think it's easy to see why convolution works in images, but remember we've kind of converted the speech recognition into something that almost is like an image. And the reason why convolution helps there, it requires a different architecture than was used for images. But the reason why it helps is, if you think about it, people don't speak at the same rate when they're saying a sequence of phonemes. So convolution on the time axis gives a little ability of the model to generalize over different local rates of speaking. And then I think the more powerful thing is the convolution that's happening over the frequency domain. Some people have low voices. Some people have high, right? We all have different pitches that are natural in our voice. And yet we could be saying exactly the same sentence. And I think the convolution gives a certain amount of correction for small variations in pitch. And again, it means the model generalizes a little better. By the way, it's not the case that you can just take speech from a low speaker and increase its speed 50% and have it sound natural. It turns out people who are naturally higher pitched speakers do different things than. So it's not like you can just correct for pitch by doing frequency shifting. Okay. So vanilla neural net, 23, 24%. Add a hidden layer, you get another 2% in accuracy. Add convolution, you get another 2% in accuracy. Is that right? 19? Yeah, another 2%. We're able to train shallow neural nets. These are neural nets with just one hidden layer. We're able to train a shallow neural net that has the same number of parameters as this and achieves essentially the same accuracy as this. So it's not a deep model. So it's better than this. It's equal to that. And it's using the same number of parameters as that. And if you let us have more parameters, we can actually train a model that's a shallow neural net with no convolution to be as good as the convolutional model. So that's a preview of where we're going. That's the basic result. Okay, so what tricks did we have to do to make that work? I'm going to talk about the 3 main tricks. One is this model compression thing, which you may or may not have heard of. Another is a trick we had to do to speed up learning. And then the other is we're going to do what you might think is an unacceptable dirty trick. We're going to do this ensemble trick. And I'll tell you about that in a minute. Okay, so model compression. Anybody heard of model compression before? This is work I did with students back at Cornell about 10 years ago. So the thing in model compression is what you're going to do is train a smart model any way you can. In this case, you're going to go to some deep convolutional architecture as deep and big as it has to be to train a smart model. And then we're going to train a smaller model to try to mimic that smart model. So we're going to try to capture the function learned in the smart model in a model that's somehow smaller. Now in this case, and when we did the work, we were really trying to take these really large models, like gigabytes in size, and compress them into models that were only megabytes in size. So small there really meant smaller in terms of size and energy consumption and speed. Here, smaller is going to mean shallower. So what we're going to do is train a deep model, and then we'll try to train a shallower model to mimic that deep model. So that's the game we're going to play. And the typical way we do this is you've trained that very smart model, and what we do is we pass, if you've got it, a bunch of unlabeled data through the model, collect the predictions of the smart model. That becomes a synthetic training set for the student model, and then you train the student on this synthetic data set with the labels from the smart model. So now it's trying to mimic, predict exactly the same outputs that the smart model would have predicted. So that's the goal. And if the student does it perfectly, mimics perfectly, and you've got a large transferred data set there, then the student model will become identical in function to the teacher model. It'll make the same mistakes, it'll get the same things right, it'll predict the same values. It doesn't have to be the same representation, right? It'll possibly have a different architecture, different size. But in terms of I/O function, it'll become the same. So that's our goal. So I'm just going to show you this graph. This is from the work 10 years ago, just because understanding this graph will make understanding the real graphs I'm going to show you make more sense. So let me show you. This is just good old root mean squared error. So this is L2 on the vertical axis. So down is good. We have some random problem here. Don't worry about it. It has nothing to do with the deep learning stuff. We've got some random problem that we've picked. And the best vanilla neural net we could train, which is actually a very good neural net. It's a carefully optimized architecture and set of hyperparameters. This model has a L2 loss just above 0.1. Okay, so it's actually a pretty good model. This would be considered state of the art in many ways 10 years ago. By doing this other stuff we did at the time where we were building these monster ensembles, the ensembles had everything in them. They had SVMs, they had boosted trees, random forests, k-nearest neighbor methods, stumps, naive Bayes. Every learning method you could think of were allowed to be in this ensemble. And the ensemble would get very large. But the nice thing about the ensemble was it could be optimized to any loss. And it could go places that no one model could go. So maybe the best single model had accuracy around here, but we could make an ensemble of the better of these functions that had much higher accuracy. And you can see the ensemble has L2 below 0.08. So it's actually a much more accurate model in this particular problem. Okay, so nothing too shocking there. I think we all tend to believe that ensembles tend to work. And the fact that one model is this accurate and an ensemble of models is that accurate presumably doesn't surprise anybody. Here's the surprising thing. It's the red line on the graph. The x-axis now means something. It's the number of hidden units that are in this neural net. This neural net is the simple neural net that has just one hidden layer with that many hidden units in it. And these are pretty small numbers, right? This is 8, 16, 32, 64, 128. So these aren't very big nets. They're certainly not big by modern standards. But even by the standards of 10 years ago, they're not very big. And here's the interesting thing is, of course, if it's too small, it can't do anything. It's not enough capacity. This model is being trained, this red model, is being trained to mimic this very accurate ensemble of models. And the sort of remarkable thing, I think, is that we get a pretty small vanilla architecture neural net to be, epsilon close to the accuracy of that teacher ensemble. Okay, and we managed to do that with just sort of 32, 64 hidden units. And that's by playing this game of passing a bunch of data through this model, collecting all the predictions that model makes, and then training a simple neural net of different sizes on that new synthetic data set. Now sure?
Roughly how much larger is the synthetic data set?
Yeah, we'll talk about that a little bit. So the synthetic data set, in this particular case, we actually didn't have any extra synthetic data. So we had to do some sort of density estimation to hallucinate extra synthetic data. And then it's roughly 100 times larger. So if there's kind of 5,000 points in the training set of these original models, think of there as being, say, 500,000 points in the capture set. And that is an important part of why it works. So I think your intuition of why this is possible is correct. Now realize we don't have any extra labels. There's no extra real labels coming from the true generating function. But we do have more data which fortunately in this case had to be created synthetically from the original training set. So the amazing thing really should be this gap between this thing and the best neural net that we could train on the original data, right? This thing gets to see the right data. This thing in some sense gets to see, it's presumably not the real targets, right? It's not the correct answer all the time. It's not like this model has 0 error or anything like that. So this thing, this red line isn't seeing sort of perfect real data, and yet it's doing significantly better than the best neural net that we knew how to train using the original data. So that's the sort of magic of this compression process, and that's being used in many different ways now. So I might have a chance to talk about that.
Sorry, just one more. The best vanilla neural network has how many hidden units?
So I don't remember for this problem. I do know that the way we were doing the experiment was we were varying the number of hidden units by powers of 2 from very small to extremely large. We were varying the learning rates. We were varying the initial weights that we applied to the model. And we were varying how far before, during, or after the early stopping point on a validation set that we would stop. So we were doing a pretty good job. Yeah, but this best vanilla neural net, it's not 10 times larger than this, and it's not smaller. It's sort of in the same ballpark. Good question. Thank you. Okay, so this extra accuracy that we get in this neural net by training it to mimic a smart model is sort of interesting, and that's the game we're going to play. So sure.
So basically, if your synthetic data set was infinite, then that red curve should not overfit, right? It should meet the blue curve.
Very good, yes. So assuming the student model has the representational power, and assuming that the learning algorithm is good enough, then with an infinite transfer set, the gap between the models should go to 0. Yes, your intuition is right on the money. Yeah.
It should stay at 0.
And should stay at 0 because there'd be no overfitting. Yeah, and whether that's real overfitting, I don't actually know. So your intuition is exactly correct. And in fact, this gap, because we don't have infinite transfer sets in TIMIT, is going to turn out to be important, and it's going to what makes me play an ugly trick.
Doesn't that contradict what you said about the representation theorem? So you said the representation only says you can achieve you can approximate the function arbitrarily well, but it doesn't mean backprop will do it. And now you say if we have a large transfer set and you have enough hidden units, then magically it will be 0.
Well, it's important both things. One that the model has the capacity to represent an accurate enough function, and secondly that backprop, the learning algorithm, is capable of doing it. If neither of those is true, then it won't do it, presumably. Yeah. So I'm not saying I'm assuming backprop is powerful enough, but if it is powerful enough, then those lines should merge and not separate. Yeah. Okay. So this is good. All right. So this is old stuff, but we're gonna see a graph like that. So let me just briefly talk about. Hopefully this is a little surprising to you that you can play this trick and train a more accurate neural net on fake data than you can on real data, right? I mean, that should sound a little counterintuitive. So let me just give you some reasons why this might work. Well, one is exactly what we were just talking about. We might have an extremely large data set that we can use for transfer to the model. The original data set might be small, 5,000, 10,000 points. Maybe now we can use 1 million points, 100 million points to do this transfer. It means that we can effectively eliminate any concern about overfitting in the student model. The student model maybe was struggling terribly with overfitting on the original training set, and now it doesn't have to worry about overfitting anymore if we have a large transfer set drawn from the right P of x, the original density. Turns out it's critical to stay on the right density. And we could talk about that later if you want. Okay, so that's part of it. There are other things, though, that are happening here that might not be so obvious. So imagine that you had 5% label noise in the original training set. So 5% of the labels, the Boolean labels, are just flipped to the wrong state. Assuming that you trained a really good, smart model, either an ensemble or a deep model, and you regularized it well, presumably it did not learn to overfit to those labels. I'm not saying it's a perfect predictor where those errors were made, but presumably you regularized well, and part of what makes that model so smart is that it's not getting all of those things wrong, meaning it's not getting them right. Okay, so it's fixed these. And now when you use it to label data, it doesn't put in the errors. The errors actually disappear. Now whether the things it replaces the errors with are the right predictions or just other predictions, that's hard to say. There's a good chance it just replaces them with predictions that aren't as confident. as the original targets. So one advantage here is that you can imagine that going through the teacher model sort of helps censor the data in a way that makes it easier for the student to learn it. So one way to think of this is, the teacher has had to work very hard to create knowledge. The student, though, doesn't have to learn to create knowledge from the original training set. The student is just learning to capture the function that the teacher had. And presumably it just intuitively makes sense that sort of creating the knowledge in the first place is much, much harder than sort of then handing off that knowledge to somebody else. So I think we're seeing instances of that. So there's also a censoring that can happen even without a label noise. Just imagine that there are parts of the space for which, given the sample size that we have and the nonlinear in that part of the space, it's something you're just never really going to be able to learn properly. It's like hard, sharp corners, hard turns in the discriminative function. And maybe it's just very hard to do that given the sample size that we have. Well, once again, the teacher model presumably will have, if it's a really accurate model, it'll have learned to do something reasonable in that part of the space. And now the student gets to see a simplified version of the original problem, which has perhaps some of these very difficult hard edges sort of smoothed off of it. So once again, the student can have a simpler problem. And one way to think about it is the function the student's learning is already learning friendly. A learning method already learned it. Whereas the original data might have been sort of challenging in multiple ways. But by the time we get to the student, we know that the function is already a pretty learnable function because it was just learned by something. Mm-hmm.
So if this argument holds, then it should be true to, you should be able to iterate this, right? And say, if I have a student of the student, then the learning difficulty has been digested twice.
Yeah, it'd be fun to talk about that in more depth than we'll be able to go into right now. We have thought about this issue. Now, for the reasons we were talking about earlier, if we do the mimic process right, the student will become equal to the teacher, and then a second iteration wouldn't buy you anything. But in the case where the student, right, because if mimicry is working perfectly, then you actually do capture exactly the same function, and then if you capture it again and again, you're still at the same place. But to the extent that there could be, like we could have a student that intentionally underfits or a student that intentionally overfits. Both are interesting for different reasons. And then iterations actually start to make sense because now you can imagine a student of a student learning to overfit less than the student overfit to the teacher's signal. And maybe we can get a sequence of models, and now you would almost do something like early stopping on the sequence. You would try to find the generation of student that is now fitting the best, yes. So I think your intuition is correct, that you could imagine a sequence of such steps, each of which is censoring the data, making the edges softer, making it yet more and more friendly as a learning function, and that maybe we would get a benefit from that. We played with it just for a tiny bit when Jimmy was here. We never saw anything magic, but it was one of the directions that we thought would be interesting to go, and we haven't gone there. So if anybody has some cool insights about how to go there, I'd love to talk about it. I think it's, whoops, oh no. Am I the first person to destroy this room? This will forever be known as Rich's stain. So actually, we should get it afterwards because it's sugar, and sugar will be sticky. So. Okay, so there's another interesting thing here that's happening, though, which is, think about it. Suppose you're doing a prediction for a medical problem. Right? Now, the risk that you might want to predict for a patient, depends on all the features that you have available to you, the history, physical, lab tests, and things like that. But it also presumably depends on a bunch of things that you couldn't measure. Maybe you can't measure the genome yet. Things you don't understand yet. We really don't understand the genome yet. And a whole bunch of things we wouldn't even have thought to measure yet. So the function that we're trying to learn might depend on the features we have available to us, but also depend on a bunch of things that aren't available to us. And that presumably makes learning challenging, for the teacher who has to create the knowledge. The student, though, by the time you get to the student model, the data is a function only of the available features. So any dependence on other features is now gone. And that's because you actually have the function there, and you're actually going to pass data through the function and capture the labels. Right, so once again, the job that the student has to do is simpler than the job that the teacher had to do in some cases. So, and then another one, which I think is very important, is You know, the original learning problem is often classification on these hard targets, 0 and 1. So you might have, 182 zeros and a single 1 someplace. Maybe some of these problems look like that. They're easy enough that you actually should learn probabilities that are very close to 0 and something very close to 1. Maybe some of these things are very hard to learn, and you really would be comfortable with a bunch of things that are like 0.1s or 0.05s, or maybe for some of these hard cases you shouldn't require that somebody actually try to achieve something which is zeros and ones. And it's going to turn out that this soft learning, learning to soft targets, we think is an important part of what makes the process work. So, okay, so summary of all of this is that the student has a simpler learning job than the teacher had, and it has a simpler learning job possibly for a number of reasons. Size of the data, the 0, 1 versus soft targets of the data, getting rid of errors, making the problem easier to learn for a function, smoother, all those sorts of things. So, yeah?
You have access to the data. Did you actually assess which of those were?
No, we're now about to do some experiments to try to do it. Some of it is easy to do, and some of it's not so easy to. If you really want a reliable experiment that you can trust the results of, some of these things are not that easy to test for. But it's definitely a direction that we need to go. Yeah. Okay, so this is the soft target. So remember, the original teacher in this case is learning a Boolean classification problem. What we do is we convert that to a regression problem, and we do something that's kind of surprising, I think, which is you might think, well, let's take the probabilities that come out of the softmax, if you're familiar with softmaxes. They basically made sure that if you're predicting like a 10 or 100 class problem, that the probabilities sum up to 1 across all of those classes. It's kind of what they're doing on the output layer of a neural net. You might think, well, let's take all these probabilities and then try to have the student learn to predict those probabilities. We actually don't do that. We go to just before the probability normalization is done to what is sometimes called the logits. And those are sort of the real values that would go into the normalization step. And we try to have the student predict these real values before normalization. And here's one reason why and it seems to help us. So when we did experiments without it, we didn't get as good results. So it might seem counterintuitive, but here's a reason why this can help. Is imagine the teacher predicts 1, 1, 1, 1, 1, 1, 1, 100, 1, 1, 1, 1, 1, 1 for something. You normalize all that and you get something like 0.01, 0.01, 0.01, 0.01, 0.9, 0.01, right, or 0.99, something like that. Now imagine that for a different case, the teacher thinks 0.01, 0.01, 0.01, 0.01, 0.01, 0.01, 0.95, 0.01, 0.01, 0.01. You normalize that, and you might get exactly the same values after normalization as the previous one, which was predicting ones and hundreds. Go further, 0.0001, whatever, 0.9999, whatever. Again, after normalization, you could get the same values. Internally, the teacher is definitely doing something different on those three cases. There's no doubt about it. It is not the same model internally for those three different cases. It's just the normalization step that then makes them look the same. To the extent that that's happening, and I don't believe that happens on all problems, but to the extent that that happens, if you want a student to mimic the teacher, it turns out it's better to give the student sort of this internal access to the raw values the teacher would have predicted before normalization hides them and then sort of makes it impossible for you to go backwards to figure out what they would have been. So it makes the learning simpler. Whether this is true on all problems, we have no idea. But it does seem to be, at least on TIMIT, was an important part of making this work. Okay. And then we just do regression. It's just good old L2 regression. We're not doing Boolean targets anymore. There's no log loss. Just good old regression, which is pretty well behaved. TIMIT, we didn't have any extra unlabeled data, and it turns out speech recognition data really depends on how you collect it, and TIMIT was collected a long time ago in a very special way. So it's not the case that we can just generate or collect more data that would look like it came from the same distribution. So we're going to do something crazy, which is we don't have any unlabeled data. We just throw away the labels on the training set. We train the deep model using the training set, throw away the labels, and then we're going to relabel it with the deep model and then train the student on that data set. So we're just going to use the same training set. So there's not even any extra unlabeled data getting used here. It's all just the original training set. And there will be a problem, and we're going to have to use trickery this is not a good way of doing compression in general. You really do want unlabeled data if you can have it. But it's good for the pedagogical purposes of this talk to do it this way. So now I'm going to show you some real results, and then we'll wrap up. So, okay, this is a graph of the number of parameters in the models on a log scale. So this is a pretty small model, 1 million parameters, 10 million parameters, 100 million. The models around here are getting sort of the size where we can't fit them in a single GPU anymore. So we have reasonably good GPUs. So these are getting to be pretty big models, but they're not like the world's largest models, but they're big. This is a shallow neural net, so it's a neural net with just one hidden layer. It has a number of parameters. We could calculate what the number of hidden units must be, I guess. It has a number of parameters that's equal to this axis. And then this is the accuracy on the TIMIT dev set. So up is good. And you can see if the model's too small, it doesn't do very well. I don't think anybody's surprised about that. You finally get to the point where you have enough capacity to do well. You start doing well. You get an accuracy just above 78%. And then, who knows, maybe the models that are too large start to overfit, or maybe that's, sorry, I don't have error bars on this. They're expensive graphs to generate. So I don't actually know if this is coming down or if this is just noise. So I think if you think of this as sort of hitting an accuracy of about 78% and then asymptoting, that would be fine. And there is a chance that if things got large enough with this training set, they would come down and overfit. I'm pretty sure they would overfit eventually. Whether that's real overfitting, I don't know. Okay. Shallow neural net, it's a model that, except for horsepower, we could have trained 25 years ago. Nothing unusual about that model. This is the model with 3 hidden layers. So this is our sort of small, deep model being trained on that same data set. And now, since we've got the same number of parameters, say, in this model as sort of those models, it means there must be fewer hidden units on each of those 3 layers for the number of parameters to add up. You've got to be careful the way you calculate parameters, right? You have to multiply by the input layer and by the output layer. But roughly speaking, you know there's fewer hidden units on these layers than there is on the single hidden layer there. And you know the magic of deep learning works. We get sort of an extra 2% accuracy just by spreading our parameters in this deeper architecture and throwing sort of a pretty good backprop at it. So that's cool. It's not unexpected. Whether there's anything interesting happening there with the crossing, I don't know. We haven't spent that much time trying to analyze what happens in the models are too small end of the graph. In fact, for the paper that we were taking to NIPS, we didn't even show them the left-hand side of the graph. We truncated it below 1. And that's because we didn't have an explanation. We didn't want people to get distracted. We didn't think it was important to the central story. But your friends, I think I can show you the whole graph. So, okay, so nothing too surprising. This is the kind of thing I think we all expected. This horizontal line, this is a convolutional deep net. So it's a deep net that has 3 hidden layers. The 3 hidden layers have about this size, I think. I think it's like that optimal architecture. But now it has convolution pooling on the input of it. And I've done it as a horizontal line. That doesn't mean it has all these different number of parameters. It's because I don't really know how to count the number of parameters. We could discuss how we want to count parameters in a convolutional model. You could talk about what's the actual number of weights that need to be trained, and that's sort of small because the weights are shared across the whole image. Or we could talk about the number of computations that you have to do at runtime. And if you're doing model compression, sometimes you're more interested in the computations, like the multiplies you have to do, than you're actually interested in the number of weights you had to learn. So I just decided to punt. It's a very good architecture. Don't worry about its size. That's not what's going to be important to us. But it's a good model. You add convolution, you get almost another 2% increase in accuracy. So take a really good one of these, add convolution, does even better. So again, the magic of deep learning. And then this is where you might start to get upset. That purple model is an ensemble of a dozen convolutional deep models. And people have discussed, I think, for example, Jeff Hinton talks about there's ensembling happening inside of these very large deep models. And I think that is true. But you can see that there's still room for an external ensemble to get more accuracy. And we didn't do anything special. We just took a bunch of models that we had trained that were all reasonably good as we were playing with architectures. And we said, oh, let's take an average of them. And sure enough, you get another % increase. Like ensembles, right, it's the gift that just keeps on giving. I mean, it just always makes sense if you can afford it. So, and sure enough, it works here. And now when people are trying to win deep mining learning competitions, they're, of course, building ensembles of their deep models. And of course, that's how they're winning. So nothing really surprising there. We weren't 100% sure that an ensemble of deep models would give us that, but it does. And I think other people are seeing this as well. Okay. Here's what I'm going to do that you might not be happy with. I'm going to train a shallow model to mimic that very smart ensemble of deep convolutional models. I'm not going to train it to mimic this deep model or that deep convolutional model. I'm going to train it to do that. And that's because I already know from previous experiments on this data set that there's going to be this gap between the teacher and the student. And the gap, I believe, only has to do with the fact that we don't have 100 million unlabeled examples. I think it has, there's no other explanation for it, I think. And it's sort of unfortunate. But if I try to mimic this and I have a 2% gap, I'm going to be right down there. So the gap means I won't be able to train a shallow model that's as good as this deep model. But if I try to train to that model and there's a 2% gap, it'll be as good as that one. And if I train to that one and there's a 2% gap, I'll actually be better than it. It'll still be an existence proof that you could train without any extra data a shallow model to have an accuracy equal to or better than a deep model and possibly as good as a deep convolutional model. It's still a legitimate test of that. It's just that I went through an intermediate state that's even more complicated than just a deep model. I actually went to an ensemble of convolutional deep models. So hopefully you won't stone me for that one. All right, so let me show you the graph. This is like the key graph of the talk. That is a shallow neural net with different numbers of parameters in it. So it's the same architectures as this red line. Like if that's above this, these two architectures are identical. Those two architectures are identical, right? So it's a shallow model being trained to mimic the very smart ensemble of convolutional models. And I think the remarkable thing is that for a reasonable number of parameters where the deep models were starting to be excellent, where they were hitting their peak performance, we're hitting a peak performance with the shallow model that's actually a little bit better than that deep model, and sort of halfway between the deep model and the deep convolutional model. And then if we're willing to give it more parameters, this is a lot more parameters. It's a log scale, right? So that's hundreds of thousands of parameters over there. We're actually able to do as well as the deep convolutional model. And remarkably, we're able to do that without any convolution in the model. That's something I never was confident would happen. I mean, convolution really is a magic thing. It's a very, very strong prior as to what the model should learn. So it's a very, very powerful thing. And the fact that the shallow model, which has no convolution in it, is able to do something comparable to a convolutional net, I think is very interesting. Had to use a lot of parameters, though, to get there. OK, so this is sort of the key graph. Yeah, and we've been looking at the dev set. Things look essentially the same in the test set, so don't worry about it. Just the same results. I'll just say this briefly. One of the key things that makes the shallow learning, shallow mimic process work is we just don't have an overfitting problem. So when we look at squared error on either the train set, the test set, or the dev set, on the shallow mimic model, it just comes down and it just never seems to go back up. So overfitting, if it does happen, happens way out there. I think that summary sort of makes sense right now. A shallow neural net can, with the same number of parameters, actually be trained that's more accurate than a deep neural net, a 3 hidden layer deep neural net. And if you give us more parameters, it can do even as well as a convolutional deep neural net. We had to speed up learning. Let me just briefly say this. The shallow models take forever to train. Weeks, months, I mean longer than we ever expected. We found that by putting a linear layer, which is kind of like a bottleneck in the neural net between the inputs and the hidden layer, that we could speed up training by about an order of magnitude. And this was very important. Now, those of you who know neural nets know that adding a linear layer in the middle of a neural net does nothing to increase its representational power. In fact, it very slightly hurts accuracy. But for us, it sped up learning by a factor of 10, and that was very important to us. So I won't go through that in more detail. I won't show you the results. But it is important that we got that speed up. The ensemble of CNNs, I think you understand that. Let me just say that, there is this issue where, so here's accuracy of the target model, accuracy of the mimic model. If they follow each other, you get a 45-degree diagonal line, right? If the mimic can do everything the teacher can do. If the mimic has less accuracy than the teacher, well, then the target has 79%, but the student only has 78%. And if it's a 45-degree line, then they still are tracking each other. The student always follows the teacher just a few steps behind. Or it could be that the slope is less and the student is actually falling behind as the teacher gets faster and better. It turns out this is for a small model and that's for a large model. If you squint, it actually is roughly 45 degrees. And there is a gap. That's why it's over on the right-hand side of this graph. So there is a gap between the teacher and the student, but roughly speaking, we don't see any sign that the student, even the small one, is running out of capacity. That means that they can't follow the teacher. And then, this is all on TIMIT.
The differences in accuracy here for the teacher are just small, right? What would happen if the teacher accuracy was like 60 instead of 80? Do you think that the whole assumption would change?
It's a good, I actually don't know. It's a very good question. Yeah, it's interesting. Yeah. Okay, this is on TIMIT. You all know not to do machine learning on one data set and draw general conclusions from it. We've done some preliminary experiments on the CFAR image classification data set. This is all I'm going to show you. A 2-layer net doesn't do very well in this data set, 50% error rate. Going to a larger neural net using dropout and some other tricks helps a lot. You get down to sort of 20% error rate. Adding convolution, multiple layers of convolution, you get much better, another 5-6% reduction. We're able to train a shallow model that has one convolutional layer, one nonlinear layer, to sort of be as accurate as this significantly deeper convolutional model. And we're now in the process of doing a much more thorough set of experiments to demonstrate that. And I think I should just stop. I just want to make sure I thank colleagues. Many of these are at Microsoft Research, and presumably you know them. So Li Deng especially helped us an awful lot with the TIMIT data set. So, thank you very much. Thank you.
Let's just take one question. Whoever wants to leave, of course, is free to do so.
And I'll be around the
Yes.
whole day, so if anybody wants to stop by and chat, I'm happy to do that. So.
One question on the
Sure.
top there.
The real message that you should be doing ensembles.
There's no doubt that
We all knew
ensembles, in fact, it's funny. So over in the applied speech group, we're starting to do things, I should say they are starting to do things where they train extremely large deep models that could never be fielded on our servers. And in a few cases, ensembles of these very large deep models, and they could never be fielded on the servers. And then we find that we can train a normal-sized deep model, which is still pretty big, that does fit on the server to mimic that thing. And we get more accuracy out of the medium-sized deep model by training it to mimic this very large, high-accuracy model than we do by training it on the original training data. And that's interesting because they have extremely large training sets as well, large labeled training sets. And they have massive amounts of unlabeled data also. So it's interesting that it's still working in that corner of the space. So now the model that you would put on the server would be a model trained to mimic a model that you couldn't afford to put on the server. And presumably the models that we might put into mobile devices would also be models that would be very small, trained to mimic these very large models. And they would be affordable on small devices. And my understanding is Google is doing the same thing. So.
Very loose connection, but what it reminds me of is say something like approximating a context-free grammar with a finite state grammar.
Oh, that's a.
You missed some certain cases, but.
Oh, that's a great analogy, and I hadn't thought of that one. I like that a lot. Yeah.
I haven't said something positive.
Sure.
Which is, to someone working on speech, the TIMIT results and your explanation were a bit, the reason people stopped working on TIMIT was because it was viewed as not relevant to real problems in speech recognition.
So it's sort of a research data set at this point that's...
It's an early attempt to try to figure out to what extent close phonetic adaptation could help with speech recognition. People moved away from that. The results are interesting because, as you say, it's hard for various reasons. But
No, that's good to know. Now, we are seeing, let's say, qualitatively similar results in the real speech recognition that we're doing with the applied speech group. But these experiments are carefully designed. There's nothing practical about this. I mean, the deep model, if you can afford to use it, you just use the deep model. Because I'm making a shallow model that has the same number of parameters. I mean, there's no real win there unless shallow is an advantage. I'm doing this to answer some sort of abstract question about whether the models really had to be deep in the first place. But we are finding on the applied work, working with real speech, modern speech data, that the compression trick often does let us train more accurate small models than we would have been able to train looking at the original training set. And I think for the reasons that were mentioned in the middle of the talk.
Thank you very much, Rich. We'll thank the speaker again.